Okay, so I'm going to be talking about artificial intelligence search algorithms on behalf of my group. But before I get to the meat and potatoes, I need to explain what a graph is because that is a central concept to these search algorithms. And this is the kind of graph that I'm talking about. So as you can see, there's no x and y coordinates. It's not like the graphs that you found in high school. This kind of graph has nodes and edges. And this is a node, and this is an edge. Nodes contain data of some kind. So it could be a number, a word, a list, or anything, really. It just depends on what the graph is for as to what data you find in the nodes. Edges link nodes together, and when two nodes share an edge, that kind of means that those nodes are related to each other in some way. So edges may have a cost associated with them. For example, the cost could be the distance between connected nodes. So here I've added the costs. That's what these numbers are next to the edges. And so this edge here from Y to Q costs 33. 33 what? Well, we don't really know. We're going to keep it abstract for most of this video. But for example, uh, maybe this graph is representing a physical space. So the edges are like streets, and maybe the nodes are points of interest that you would want to travel to. And so maybe this 33 here is saying that this costs that this is 33 kilometers long, or maybe it's saying it takes 33 minutes to drive from Q to Y, right? Um, so it could be used in lots of different ways. Now, graphs have child and parent nodes. Child nodes are at the level immediately below the parent node and are connected by an edge to the parent node, and parent nodes have children. So here, A is a parent of D, and so that means D must be a child of A, and A is also a parent of B and Q. But A is not a parent of Y. Um, A is an ancestor of Y. If you want to call it a grandparent, you could, but let's not complicate things. And so equivalently, you can say that Y is a descendant of A, but it's not a child of A. And then what relationship do B and D have with each other? Well, they're on the same level, so we call them siblings. So because they have the same parent, right? And they're on the same level, so they're siblings. And so also Q is also siblings with these nodes. So for these search algorithms, um, they all have some commonalities. So you're going to search the graph for the goal node, and you start searching from the start node. And throughout the algorithm, you're going to visit nodes. And during each visit, you're going to check if the node is equal to the goal. And the solution is the path from start to goal. So let's do breadth first search. So here are the steps of the algorithm. So visit all children of the start node in search of the goal node. Visit the children's children in the same manner. Continue the process until the goal is found. However, when I go through these algorithms, um, we're not going to worry about where the goal node is, although it is important for the algorithm. So, so here's our start node. So let's do a breadth first search on this graph. So 0 has these children, so I'm going to visit them in order. 1, 2, 3, they're visited, and okay, 1 has these 2 children, so visit them in order. 4, 5. 2 has these 2 children, so visit them. 6, 7, and we are done. So on the pros side, it always finds the answer, assuming there is one, and it's guaranteed to find the shortest path, and that means it has the fewest number of edges possible. On the negative side, it's a bit inefficient because it takes up a lot of memory. So let's do depth first search. Search the descendants of a node before searching neighbors/siblings. Go as deep as possible, then backtrack to previous level. Repeat the process on unvisited children, and let's do it. So we start off by visiting the start node, number 1, and I want to go a level deeper, so let's visit 2, and I want to keep going deeper, so I'm going to visit 4, not 3. So I visit 4. Now 4 doesn't have any children, so I can't go any deeper than that, so I return to 2, and I see that 2 has an unvisited child, so I'm going to visit it. So I visit 5. 5 doesn't have any children, so I return to 2. 2, I've visited all of 2's children, so I return to 1. And I see that 3 hasn't been visited, so I visit 3. Pros and cons. So pros, it doesn't require too much memory, and it can be fast, but it depends on the graph. Cons may fail to find the goal, and it may get trapped in an infinite loop. Iterative deepening search is like depth first search, but search only up to depth D. Depth means how many levels down a node is from start. Start node has D equal to 0. If goal not found during a depth D search, increment D and search again. Every depth D search begins at start node. So let's begin. A depth 0 search, visit A, and we're done. We didn't find the goal node, so do a depth 1 search. Visit A, B, C, D. Didn't find it. Let's go to depth 2. Visit A, B, E, F, C, G, D, H. And we still didn't find it, so we're going to have to do a depth 3 search and not find it, and then a depth 4 search and find it. Pros, it doesn't take too much memory, and it finds the shortest path. Cons, if it is known that the goal will be deep in the graph, a depth first search may be faster. Okay, lowest cost for a search, also known as uniform cost search. So visit all children, calculate the total cost required to visit those children. For the child that was cheapest to visit, visit its children. Factor the new edges into the calculations as you go along. Repeat until all nodes have been visited. Solution is the cheapest path. So I want to get from Sibiu to Bucharest. So first, after visiting Sibiu, I go to this guy because it's cheaper for me to get from Sibiu to here than it is for me to get from Sibiu to Fagaras. So I visit here. And next, I visit Petesti because it's cheaper for me to get to Petesti than it is for me to get to Fagaras. So I visit Petesti. Um, Now, I'm gonna visit Fagaras because it's cheaper for me to visit uh, Fagaras than it is for me to visit Bucharest. So I visit Fagaras. And next, I'm going to visit Bucharest from Petesti because that is cheaper than visiting it from Fagaras. And so we had this second path going here, but it didn't end up working out. So what the solution that we found is this path to Bucharest, and it is the cheapest path. So pros always finds the cheapest path. And it can't be trapped in an infinite loop. Cons, it is slow, and it takes too much memory. Heuristic depth first search. So a heuristic is a rule of thumb. It provides a decent solution without having to think too much. So use a heuristic function called h of n. H of n accepts nodes as input and outputs its guess of the cost. Visit the child with the lowest h of n. Repeat on its children like in depth first search. So here we've got the graph that's going to be searched. We have our start and goal node, and these red numbers are those are the calculated heuristic values from h of n. These are costs on the edges, but we don't care about those. Okay, the algorithm is not going to look at those at all. Okay, so so we start off, we visit S, and then we visit C because 7 is less than 10 and 7 is less than 8. Keep going deeper, visit F because 1 is less than 6. Visit G because 2 is less than 3. And we visit the goal node. So this is our solution, but this here is the optimal solution. So we can see that this algorithm, it got us a pretty good solution, but not the best. So pros, it's fast, and if h of n is reasonable, it provides a reasonable solution. Cons, not optimal, and can get trapped in an infinite loop. This would be a depiction of that. Greedy best first search. So it's called greedy because it tries to select the best node at every step without concern for whether this leads to the optimal solution. So why is that called greedy? Well, it's sort of like if you're greedy, you're trying to do a get rich quick scheme, and you're not really thinking about the long-term future, right? You want the money now. So that's kind of what this algorithm is like. So we visit nodes with the lowest heuristic value. Nodes visited don't need to be children, just adjacent. Repeat until the goal is reached. And so here, we're trying to get from Arad to Bucharest. And so we start off by visiting Arad, and then we visit Sibiu because 253 is the cheapest here. And then from there we visit Fagaras, and from there we visit Bucharest. And so this is our path. Pros, it's fast. Cons, not guaranteed to find the best solution, and it takes too much memory. A-star search. So visit children that have the lowest f of n value, and f of n is the cost of the path so far, plus the heuristic value. Cost of the path so far is the total cost of the edges, similar to lowest cost first search. H of n should be an admissible heuristic, which means that h of n is never greater than the real cost. So remember, our heuristic is just a guess at the cost. So we want the heuristic to never overestimate the cost. And this algorithm is commonly used in video games for NPCs to find their way in the world. So we want to find the best path from A to J, basically the cheapest path, the path of least resistance. So in red we have the heuristic values, and in brown we have the costs. And so we start at A, and we look at our children B and F, and we make some calculations. So for F, we say 3 plus 6, that's 9. And for B, we do 6 plus 8, that's 14. And so we see that F is the cheaper one, so we visit F. Looking at F's children, we make some calculations on them. So for G, 3 plus 1 plus 5, that's 9. And for H, 3 plus 7 plus 3, that's 13. So we see that G is cheaper. Visit G. We're forced to visit I, so let's visit I. And we can travel to H, J, or E. And it's worth noting that J has a heuristic value of 0, since it is the goal node. And so we do our calculations similar as before, and we find that J is the cheapest. So visit J, and we are done. And that is the best path, the cheapest path from A to J. So pros, it's fast, and it always finds the best solution, provided that h of n is admissible. Cons, it takes too much memory.